The core logic of hypothesis testing comes down to 5 steps. Step 1, you need to determine your hypotheses that you are going to be making inferences about. Step 2, you need to determine what you're going to be comparing and the characteristics of what you're going to be comparing when you do your inferential analysis. Step 3, you have to determine the cutoffs you're going to use to test the significance of your hypothesis. Step 4, you have to calculate the test statistic that you're going to be using. And step 5, you're going to compare what you calculated in your test statistic to your cutoff. These 5 core steps make up the logic of the rest of this class. So master these 5 steps and you've got a long way towards understanding the reasoning behind everything that we're going to be doing moving forward. Once you master the logic of this, it mostly comes down to calculation. So the first step is we have to take whatever our research experiment is, and we have to reframe it into 2 key hypotheses. The first is the research hypothesis, the second is the null hypothesis. The research hypothesis is that our data has an effect because of our treatment or because of whatever we're looking at. There's a reason why we think our data is different, right? It's because whatever we're looking at has changed or altered our data. The null hypothesis says it did not. That if there is any difference in our data and the general population, it's because of research random sampling alone. Right? In other words, the null hypothesis says that whatever we did, whatever we looked at, had no effect. Right? So the research hypothesis says it did have an effect. The null hypothesis said there is no effect. When we're talking about a research hypothesis, we have to break it down into what we call 1- and 2-tailed hypotheses. 1- and 2-tailed hypotheses basically come down to whether or not our hypothesis has a direction. Right? So if we think a particular drug increases your concentration, right, our research hypothesis is that the drug increases concentration. And notice by saying that it increases, right, we're saying it has an effect, and that effect is to increase it, we are giving it a direction. So it's moving in a particular direction, it's increasing it. If, on the other hand, we said a drug decreases the need for sleep, right, we're saying that it's a direction. We're saying decrease, but that is still a direction. Non-direction is we don't know what the effect will be. For example, we might be interested if there's some sort of change in the environment and its effect on productivity. Let's say that you add a foosball table to the office, and you're wondering, is that going to affect productivity? But you're not really sure. Maybe it'll decrease it because everybody's playing foosball, or maybe it'll give everybody something fun to do and motivate them and increase morale, and it'll increase productivity. In this case, we're not quite sure what effect the foosball table will have, but we're pretty sure it's going to have an effect. Since we don't know whether or not it's going to increase or decrease productivity, right, we still think it's going to have an effect. Right? We're still saying our treatment, our change, adding the foosball is going to have an effect. We just don't know which direction. We call that a non-directional or a 2-tailed hypothesis. This becomes important when we're looking at our cutoffs because we have to look at either one end of the distribution or the other in a 1-tailed test, right? Because we're only looking at either greater than or less than, increase or decrease. Whereas in the 2-tailed test, we're looking at both ends. And this is going to be important in the cutoff, which we'll talk about here in step 3. Step 2 is to determine the characteristics of what we're comparing our data to. This is almost always going to be the null hypothesis, right? What we're asking is we are determining whether or not the null hypothesis is true, right? Oftentimes what we're saying is, could I have gotten my data by random chance alone? Is random chance a sufficient explanation for what I have here in my data? If so, then the null hypothesis is true that there was no effect. So I'm comparing my data to the null hypothesis. That's the comparison distribution. So we have to usually ask what the null hypothesis distribution looks like. For step 2, you don't have to do a whole lot. For right now, I'm going to be giving you the information for step 2. As we move through the course, we'll be calculating the information for step 2. Step 3 is we have to determine the cutoff at which we are going to reject the null hypothesis. What is the point at which our data becomes so unlikely that it can't be due to random chance alone? That I don't think it's just a sampling effect that I got those scores? How extreme, how far away from the mean of the distribution does it have to be? This is a bit of a judgment call. Right? We can have different levels of significance, different levels of a threshold, of a cutoff, and there's really no right answer. At which point is something so unlikely that we can reject that occurrence? You might say 1%, someone else might say 10%, you might disagree. This is one of those things where, again, it's more about an argument, right? But you have to have a set threshold before you do anything. You have to establish from the beginning what your cutoff is going to be. In psychology, we tend to use the 5% cutoff rule. And this is sometimes this magic idea of 5% that emerges. That means about 1 out of 20 times I'm likely to get this data by chance alone. And we say, nope, that is too unlikely, and therefore I reject the idea that it became from random chance alone and it had to be due to my treatment. Maybe 1 out of 20 is just too common for you. You think it's just too likely, and you want to go to 1 out of 100 or 1 out of 1,000. The choice is up to you, but the smaller percent chance you allow it to be, the harder it is going to be to detect. We will generally be looking at about the 5% cutoff in this class. That's what the field tends to use. The threshold is not just about the percentage, though, right? We have to compare it back to the statistic we're going to be calculating. And since we've learned how to do the z-score, we'll be using the z-score to start with. So we have to know what z-score corresponds to my percent cutoff. This is where we can use that table in the back of the book. There's also a table in chapter 4 that can show you, for example, the significance calculation at 5% can tell you the z-score is going to be 1.64 or negative 1.64 for a one-tailed hypothesis. For two-tailed, it's 1.96 and negative 1.96. Right? Notice that we have to go further along in the z-distribution for the two-tailed hypothesis, because what we're doing is we're looking at the two tails. In the one-tail hypothesis, it's 5% all on one side. However, in the two-tail hypothesis, we have to split the 5% between both tails, so it's actually 2.5% greater, 2.5% less, which means that we have to go further away from the mean. So if you're going to use that 0.05% cutoff, you can just use the 1.64, 1.96 cutoffs. You can see here we also have the 1% cutoffs, or you can use whatever percent cutoff you want and just look up the score in the z-table in the back of the book. So once you have determined your research hypothesis, your null hypothesis, you have determined the characteristics of your comparison distribution, and you've determined your cutoff or your threshold, the next step is to calculate your statistic. In this case, we'll be calculating the z-score. Once you've calculated the z-score, we go back and we compare the z-score to the cutoff that we determined. And if the z-score is more extreme, if our calculated z-score is more extreme than the cutoff, then we move on to step 5, where we can reject the null hypothesis. We say it is too extreme. We reject the idea that this came from random chance alone. If, on the other hand, our z-score is less than the cutoff, when we move to step 5, we fail to reject that hypothesis. We fail to reject the null hypothesis. In other words, random sampling alone could account for the effect that we are seeing, so we fail to reject. So comparing the z-score that we calculate to our cutoff is going to determine whether or not we reject or we have to accept that null hypothesis. Those are the 5 steps to hypothesis testing. Let's see an example of them in action.